Have you ever wondered how a robot moves with such precision and grace, performing complex tasks without jerky, inefficient motions? It is a fascinating blend of mathematics and engineering that makes this possible. A crucial part of that graceful movement comes down to something called robot trajectory generation. This is the process of planning the robot's path through space and specifying its motion over time, including positions, velocities, and accelerations. When we talk about types of trajectory generation, we are primarily looking at how these motion profiles are mathematically created to achieve specific goals. The most common approaches include point-to-point trajectories, joint space trajectories, and task space or operational space trajectories. The core reason we have different types is to balance between simplicity, computational efficiency, and the specific demands of a task. For example, point-to-point trajectories are often the simplest to compute. They focus on moving the robot from a start configuration to an end configuration, typically optimizing for time or energy without necessarily defining the path between these points. This approach is very efficient for pick-and-place operations, where the exact path does not matter as long as obstacles are avoided. It often uses polynomial functions like cubic or quintic polynomials to ensure smooth transitions in velocity and acceleration at intermediate points, which prevents sudden jolts. Joint space trajectories define the motion of each individual joint of the robot independently. Each joint follows a predefined path from its starting angle to its ending angle, and all joints complete their motion at the same time. This method ensures that the robot's joints move smoothly, but the resulting end effector path in Cartesian space might not be a straight line. This type is generally easier to control because each joint's movement is decoupled from others, simplifying the underlying control system design. This is particularly useful when you need to guarantee smooth and predictable joint motions, such as for industrial manipulators performing repetitive tasks in a confined workspace. On the other hand, task space or operational space trajectories define the motion of the robot's end effector directly in the Cartesian space, that is, in terms of x, y, z coordinates and orientation. The robot's inverse kinematics are used to calculate the necessary joint angles to achieve the desired end effector path. This allows for straight line movements or complex curves in the workspace, which is critical for applications like welding, painting, or surgical procedures, where the tool tip must follow a precise path. While offering greater control over the end effector's path, it can be more computationally intensive and may encounter singularities, which are configurations where the robot loses a degree of freedom and cannot move in certain directions. To decide which type is best, engineers consider the application requirements. If the primary concern is the final position and avoiding obstacles, point-to-point or joint space trajectories might be sufficient and more computationally economical. However, if a precise path in the environment is paramount, then task space trajectory generation becomes indispensable. For instance, when choosing a trajectory, you might encounter terms like via points, which are intermediate points the trajectory must pass through, or blends, which are smooth transitions between trajectory segments. These are crucial elements for defining complex and fluid robot movements. Ultimately, understanding these different types of trajectory generation allows roboticists to intelligently design robot motions that are not only efficient and safe, but also precisely tailored to the demands of diverse applications, ensuring robots can perform their tasks with optimal performance and reliability.
If you love robotics, like, subscribe, and keep building with us.